I'm Professor N.K. Pandey from Department of Physics, University of Lucknow. And in today's session, we are going to discuss on a very important experiment of quantum mechanics, the Davisson and Germer experiment. Now, before this experiment, Compton effect and photoelectric effect were able to establish it beyond doubt that the electromagnetic waves could behave like particles. And because the nature is symmetric, therefore it was also expected that even the particles under certain circumstances could behave like waves. And Davisson and Germer experiment was able to establish that electrons exhibit diffraction when they are scattered from crystals whose atoms are spaced appropriately. Now, this is Davisson and Germer experiment, and we have a small schematic diagram shown in the figure. And you can see we have an electron gun that is giving the electron. They are being accelerated and being targeted on a nickel. So this is the incident beam at a different potential difference. And this is the scattered beam. And this is the electron detector that is detecting the intensity of the electrons. This apparatus had the facility to vary the energy of the electrons in the primary beam, of course, by changing the potential difference, the angle at which they are incident upon the target, and the position of the detector. Now, according to classical physics, the scattered electrons should emerge in all directions with only a moderate dependence of their intensity upon a scattering angle, and even less upon the energy of primary electrons. And in fact, when the experiment was performed, in the scattered beam, there was a uniform distribution of electron intensity, confirming the classical physics hypothesis. However, during the experiment, an accident occurred. The whole experiment was being done in an evacuated chamber, and during the experiment, somehow some air seeped into the apparatus, and it oxidized the metal surface. Now, naturally, for experiment to be done, the nickel surface had to be deoxidized, and for that, to reduce the oxide to pure nickel, the target was baked in a high temperature oven. After hitting the target was returned to the apparatus, and the measurements resumed. Now, what happened after the baking in the experiment? Now, instead of a continuous variation of a scattered electron intensity in the scattered beam, with the angle, distinct maxima and minima were observed. Now, the positions of these maxima and minima depended on the electron intensity. Now, this was completely a surprising result, because the maxima and minima are the properties exhibited only by the waves and not by the particles. And here they were observing the scattering of the electron beam and not that of a wave. So this maxima and minima was something that was surprising, and that we need to explain right now. Here is a polar graph of electron intensity. Now, this is incident beam, and these are the different accelerating voltages of the electron. For example, for one such 54 electron volt, this angle is shown to be 50 degrees. Now, this graph is plotted in such a way that intensity at any angle, for example, the intensity at 50 degrees, if we consider, the intensity at any angle is proportional to the distance of the curve at that angle from the point of a scattering. That is, we are talking about this particular distance from here to here. So for different distances, the intensities are different at different angles. So this is how the polar graph has been plotted. And this is again the same for 54 electron volt. This is how the maxima and minima are observed when a plot is made between the intensity and the accelerating voltage. Now, what is the reason for this new effect of maxima and minima in the electron beam scattered? Why did it not appear until the nickel target was baked? Now, let us see this. The Broglie hypothesis suggested that the electron waves were being diffracted by the target much as X-rays are diffracted by Bragg reflection from crystal planes. The effect of heating a block of nickel at high temperature caused many small individual crystals of which it was composed to form into a single large crystal all of these atoms got arranged in a regular lattice. That was the effect of heating the block, like this one. You can see that this is the lattice, and these are the points at which the crystals are located, and this is the interplanar spacing, and we have the Bragg reflection taking from these planes here. We have the electron being incident, and this is the reflected beam, and this is the lattice spacing. So this is the complete picture of how the small individual crystals got into a single large crystals, and all of them got arranged in regular lattice. So we have the Bragg reflection taking place now of the electron beam from the nickel target. Now, can we verify that the Broglie waves were responsible for the findings of Davisson and Germer? Can we verify that? Then let us consider a beam of 54 electrons. Maximum for 54 electron volt occurred, as we have seen, at 50 degree with the original beam, as you can see from this figure. To repeat the figure, the angle of incidence and scattering relative to the family of Bragg planes, if calculated, will both be 65 degree. Because in the formula we need the angle from the family of Bragg planes. Now let us use the Bragg equation for maxima in diffraction pattern. N lambda is equal to twice A sine theta. Now here A interplanar spacing is 0.91 angstrom, theta is 65 degree. Assume N is equal to 1, then the Broglie wavelength lambda of the diffraction electron will be N lambda is equal to 2A sine theta. Then lambda as calculated for the experiment will come out to be 1.65 angstrom. Now this is the value. You must remember that we have got it through the experimental value for 54 electron volt energetic electron. Now let us calculate the same wavelength from the Broglie formula, that is lambda is equal to h upon mv. To calculate the expected wavelength of the electrons, we use the formula of kinetic energy T is equal to half mv square. We have not used the relativistic formula, as the electron kinetic energy of 54 electron volt is small compared to the rest energy of 5.1 into 10 to the power of 5 electron volt for the electron, and so we ignore the relativistic consideration. So the momentum comes out to be mv is equal to a square root twice mt. So the electron momentum, if we put all the values over here, it will be 2 into 9.1 into 10 to the power of minus 31 kg into 54 electron volt into 1.6 into 10 to the power of minus 19 joule per electron volt. So this is the momentum, and that on calculation comes out to be mv is equal to 4 into 10 to the power of minus 24 kg meter per second. So if we put this value into the Broglie wavelength to calculate the wavelength, then lambda is equal to h by mv is equal to 1.66 angstrom. Now the electron wavelength here is therefore in excellent agreement with the observed wavelength, that the observed wavelength was 1.65 angstrom, as you can see from here, 1.65 angstrom. And now what it should be for the Broglie, according to the Broglie formula, is 1.66 angstrom, strikingly the similar value. So that means the Davisson and Germer experiment demonstrated the wave nature of the experiments, confirming the earlier hypothesis of the Broglie. And here the electrons were behaving like waves, and that is why their diffraction from the nickel target was just like the diffraction of a wave, and therefore in the scattered pattern we got maxima and minima in the electron intensity. Thank you for your kind attention.